Hey, everybody. All right. So, Gutsy David made a post, I think, last night on this talk that Mike Acton gave at sorry, can't talk, CppCon, Data Oriented Design and C++. And I started watching it last night, and it's very inspiring. I like it quite a bit, and I would like to talk about it, give you some of my responses on these things. And so I'm going to record just one long session with me watching this lecture, this talk, and I'll pause it at various points to share some thoughts that like I strongly agree with, or I disagree with, or I have an additional view or something. And this is probably going to, well, the video itself is an hour and a half. And then with my comments, it's probably going to be 3 hours or something. So I'll cut it off at the 50-minute mark, just again, so YouTube will translate to all the languages, and then you'll get multiple parts. So this is my plan, and I wanted to share with you that before I do this, as I always try to do, I just want to set the stage here, is I'm always trying to foster goodwill, and my goal here is not to pick on Mike or disagree with him. It's actually to just potentially provide additional context and share what I think. I know a little bit about him. Sadly, I've never heard of him before last night, but I appreciate Gutsy David, you leveling me up, and now I know about him. And the best I can tell, I watched maybe the first 30, 40 minutes of this. This guy absolutely knows what he's talking about. Totally knows. Like, this is a seasoned veteran. He's an expert architect, developer. There's all the things he's talking about send me a signal that this is a very serious, elite, world-class coder, technical leader, architect, all that stuff. So I want to start there and say that he's probably right from his lens on almost everything. The things that I'm probably going to share that I was kind of thinking of last night are more related to things that might be slightly different if his lens is different. And that's the context that I want to share. Now, one of the big things is, as I think many of you know, I created Nautica when I was 25, and I'm just sharing this to give some background so we're all on the same page, is I did write several million lines of code in C++. It started as C because I wanted to learn C more, and then pointers. So then I shifted it to C++, and I learned a lot. And from there, I've I code in a lot of languages. I consider myself more as a generalist today. I just Golang, JavaScript, Python, C, C++, C Sharp, Java, Lua. Actually love Lua. So I love all languages basically, and I try to find a way to use the best tool for the job. That's my goal. Now, that being said, C++ is my favorite language. That if I can, I want to be just super clear. If I can find an excuse to code in C++, I will. And then sometimes I can't make a good enough excuse, so then I code in Python, and it makes me sad a little bit. Not that Python's not great. It's just I like doing templates and things, and yeah. So the reason why I share this is, while I've done video games, just like it sounds, as Mike Acton has, I've also done a whole bunch of other things. So I've built parallel computing things. I've built neural network frameworks. I oversaw the development of sort of these 2 mobile games at Machine Zone. This is Game of War and Mobile Strike. Now I didn't do, just to be clear, I only did that for a year. So most of the development was from other folks, but I did sort of oversee engineering for a brief period of time, about 70, 80 engineers, right? And then I've also led teams of PhDs in research and prototypes and architecting the Merli system, or the mentor system, and building the foundational elements of Merli's AI. So the point of this is not, I'm not trying to flex. I'm just trying to share that I have not just focused on a single dimension. I've kind of focused on a whole bunch of things. So my perspective on these things might be slightly different simply because the lens that I have, it's a widening of the aperture. So that's really all I really want to do here, is potentially widen the aperture, because I think that for games, me having worked in this space on my own and then at Machine Zone, and I love games, right? I think at one point you saw my Steam stuff. Check out Enshrouded if you haven't already. So that's kind of the point of this. And now, without any further ado, I'm going to start. Oh, sorry. I have one more thing to say. I'm going to get things wrong. I'm not the knower of all things. I'm going to say stupid things. I don't get embarrassed, but I don't generally edit these things out. I do edit out sometimes if I make mistakes on bleeding edge things, because the likelihood that someone will fact check me is small. So I did that in one of these videos. Is I made the wrong statement about something super, super nuanced with AI that other people might miss. So I edited that out. Now, in this talk, for mistakes that I make, I'm probably going to leave them in, because I know there are experts in the community like Gutsy David and Untranslatable Metaphor and Alexi and so on and so forth, Empty Code. I know there's experts, and you guys will call me out, and I like that. I want that. And it's really important, I think, especially for those of us that are senior, to show less senior people that we make mistakes. So they know that, like, even the people that are supposed to get all this stuff right, they don't. And it's a fallacy to pretend that we do otherwise. And I think that by showing openly that we make mistakes, I think it actually lowers the bar for entry for new developers, because a lot of them are terrified, right? I was terrified when I saw these titans at first. And so I leave the mistakes in on purpose, because I just want the younger audience, the people that are not at Gutsy David's level or Untranslatable Metaphor and Alexi, right? I want them to be able to see that, oh yeah, Goju gets stuff wrong all the time. And I try my best to always own that. So I'm gonna get stuff wrong here, not on purpose, but because I just don't know everything. And so please keep that in mind. And seriously, please fact check me in the comments, just like Alexi has done, just like Gutsy David is doing. Untranslatable Metaphor, I don't think he can stop himself from doing that. And then it levels all of us up. So let's get started.
I want to introduce someone who's going to introduce our keynote speaker. I want to bring up Alex Rosenberg. He's the manager of platform architecture for Sony PlayStation.
By the way, I think that's John Kalb, and I have worked with him a lot when I was doing BoostCon C++ stuff. Great guy.
So I got asked who from the games industry should come talk to this crowd. The games industry is largely, the console game industry is largely C++ based. So really there's only one name for me, and that's who we're going to see today, Mike Acton, who is engine director at Insomniac Games. I don't know if you know their titles, but they've done some like Resistance and Ratchet and Clank and Fuse and Sunset Overdrive is their new one. They pretty reliably put out 2 console games a year, which if you have no frame of reference is a Herculean effort. Hundreds of people are involved in these things, and getting it to all happen on schedule is very challenging. And that's a core part of what Mike does there. He's also been responsible for quite a bit of technology sharing in the games industry. First thing I have in my head is the Cell Performance website, which was for people who were working on the cell chips that we used in the PlayStation 3, as well as researchers who were using them. And then more recently, Mike did Alt Dev Blog a Day, where he encouraged people from the games industry to write a single blog entry each day on a common shared website, so there was always something to read. And as well, on Insomniac's page, there's papers on various research they've done and things that they've had success with. It's all been fascinating reading. And with that, it's my pleasure to introduce Mike Acton.
Thanks. Hello, everybody. Thanks, Alex. So yes, I'm Mike Acton. I'm Engine Director at Insomniac Games. How many people here are game developers? Okay, so that's a relatively small minority of you. So I want to give a little bit of background, anticipating that, on what I do, what our team does in the context of making games. So we, as a team, generally build the runtime systems, especially the systems that require the most performance, are the most used in a game as far as the amount of data that's being transformed. So examples are the rendering system, animation and gestures, streaming cinematics, visual effects, post-effects, navigation, localization, basically all the big kind of systems that are not specifically the game itself. We also do all the development tools. So the tools that we use inside the studio as a studio to make the game. So the level creation tools, the lighting tools, the material editing tools, visual effects creation tools, animation, state machine tools for our animators, visual scripting, scene painting, cinematics, tons and tons of tools, hundreds of tools that we make and develop as a team to let the rest of the team, sort of the hundreds of people, as Alex mentioned, who are working on releasing our games. So we're both on the console and very concerned with the characteristics of that machine, as well as on our PC development side, in concern with the characteristics of our development machines. So I wanted to give you an idea sort of our values and the things that are important to us as we are developing these things. So hard deadlines are critical to us. We know when we're going to ship a game to the day. I can tell you right now, Sunset Overdrive will be on the shelf on October 28th.
Just real quick, one of the things I really like about Mike Acton is he's pretty particular in his precision when he's talking about certain things. I from what I saw from earlier segments, and I want to just clarify a couple things. Is his word here, hard, in front of deadlines, which is similar to what he's going to talk about shortly with real-time systems, which he uses, I believe, the word soft. Hard deadlines and hard real-time systems have a fixed endpoint that cannot be changed. That's sort of what is implied by the word hard. Soft deadlines and soft real-time they have this preferred deadline, but it's not, if you miss it a little bit, everything won't blow up. But hard deadlines are things like you cannot miss it, and hard real-time systems are things you must adhere to. So just a little background. I'm going to pause for just one quick second, and then we'll continue. Alrighty. Is it recording? Yeah. Okay. Let's continue.
And when you know those dates within a very small window, well in advance of shipping the game. And so we have multiple games in flight. We know when they're going to ship. We have millions of dollars in marketing money, depending on the pipeline of shipping that game. So there's no missing this. There's no flexibility here. It ships. It's on the shelf on this day. A couple of years in advance, roughly, when it's going to ship. So you have to scale the fit. You have to make sure it's going to work. Soft real-time performance requirements. So generally speaking, as a game, that's going to either be 16 things within a frame, or either going to be 16 milliseconds.
By the way, just to share an additional piece for those of you that may not be seasoned veterans, when he's talking about the hard deadlines, oftentimes what we do in these cases is we build the schedule backwards. So he's told by his executive leadership or someone that the game must ship in 2 years. And so that's fixed. And then we start to work backwards on, okay, so right before the game, this must happen, and then before that happens, this will happen. And so you generally just, at least this is what I tend to do, and some of the other folks I work with do. So I just wanted to add a little bit more detail that what he's describing is very much a common thing that we sometimes need to deal with in developing projects and software systems that have fixed hard deadlines that are known in advance.
Milliseconds or 33 milliseconds roughly. And that's the kinds of time frames that we live in. Generally speaking, when we're looking at anything in particular, we're going to be talking about microseconds. And if we're talking milliseconds, we're talking about fairly large sets of transformations, very significant systems. But generally, when we're looking at things, we're talking in microseconds. So that's the kind of time range we're talking about when we're talking about our game performance.
Just to add a little bit more detail, in Nautica, we have what I call pulses, and there are 10 pulses that happen every second. So essentially 100 milliseconds. And those are essentially also soft real-time requirements. And what happens is sorry, I forgot to close some stuff. People are pinging me. What happens is in each of those pulses, Nautica must do a bunch of things in order for the whole world to stay doing its stuff. So just to give you additional context about his 33 millisecond thing, other games that I've worked on and other critical systems that have even hard real-time requirements will often have these types of things. And you generally, if you miss them by a small margin for the soft ones, it's often not that big of a deal. But with hard ones, you cannot miss them at all. But if you miss them by a lot, things will really start to go in the wrong direction really fast. So I love that he's setting this up as the background.
Usability, we have so many people trying, build a game, build it rapidly. Huge games, hopefully much bigger than is represented by the actual number of people on the development team. So we need to make sure that our tool side and our system and everything, both for the programmers and for the non-programmers, the artists, the designers, sound engineers, et cetera, are easy and quick for them to use. Performance in general is critical to us. The faster that anything is, either a process or some system running on a piece of hardware, the more space you have for other things. And that's critical to us. We want to solve new problems, and in order to solve new problems, we have to make space for them. And as I said, we have that window in a frame that's 16 milliseconds or 33 millisecond space. And so if we want to put more stuff in there, we've got to make space for it. Performance is king. Maintenance in general, we have to maintain it. We have to continue. We have multiple games in flight. We continue with the development of the engine and tools over time, over games. So we have to make sure it's maintainable from our point of view. Debuggability, again, we have hard ship dates. We have to make sure that we can solve problems, right before gold, right when everything is coming together, that those things get solved quickly. So being able to reason about what's gone wrong is crucial to us. What languages do we use? As Alex said, the industry is dominated by C++, and that's no less true for us. But we do use a lot of other languages in the mix, a little bit of C, a little bit of assembly, Perl, JavaScript, C#. Obviously not all of these on the actual console target, but on our piece of development side. I'd say for our whole code base, C++ probably represents about 70% of our code base. That's a rough estimate. I didn't actually count lines of code or anything. Certainly our most preferred target would be assembly. Like that would be the thing that we would love to just work in all the time. But reality, of course, means that we use tools that help us do that rather than doing it directly for all the things, especially at scale. There's also random.
Just a small additional piece. For some of the work that I've done, especially for software transactional memory, oftentimes I will have to get to the assembly level. I also in Nautica had to get to the assembly level a couple times, and I can code in assembly, but boy, oh boy, I will avoid that until it's absolutely necessary, because while it is extremely fast, one, I think it's super hard. And on top of that, once you get to the assembly level, the number of people that can maintain assembly or write assembly that does what it's supposed to do as fast as it does it feels as though that's a shrinking number every day. So I get what he's saying, and this is one of the core challenges with writing video games is they need to be screaming fast. Performance is king, like he's saying. It absolutely is. I know where you're coming from, brother. And I also understand the need to drop down into assembly. But, yeah, that just brought back some nightmares for me.
Some other things, pixel shaders, vertex shaders, all that sort of GPU stuff, geometry shaders, compute shaders, a lot more work going on in this space now. And to connect with the keynote yesterday, we definitely don't make games that go to Mars, but there's a lot of similarities between what we do and what I understood that JPL did in their embedded system for the rover. So how are games like the Mars rovers? Exceptions. In a similar way, we avoid them. We turn them off if we can at all help it. Occasionally there's a...
Okay, let me pause this for a second. I need to disable these other messages because they're becoming a distraction, but just give me 1 second. Okay, we're back. So this is maybe the first point that I want to talk about. Exceptions. This is a very complicated topic, and we probably don't have time to discuss this in great detail. I don't think I know what the answer is, but I think it's very important to understand the trade-offs here. Is historically, prior to using exceptions, the way that errors will propagate or you'll handle things is you return a integer or something that is like the error no. And in the C world, it's sort of like, I think, 0 if there is no error, and anything else is some kind of error. So you sort of like not it, and that gives you, if you're in a good state, and then if it's a bad state, then you look at the error number, blah, blah, right? So why is this not acceptable? Well, what also happens is, for certain cases, it will set a global variable that is the error no, okay? So you have this global int error no. And this is going to be set to some value. So if an error happens and somebody misses it, you can just look at it. Well, once you start to have multiple threads of execution that are working in tandem, and they're both writing to this, what do you do, right? What you do is exceptions, right? Because exceptions allow each of the threads of execution to have their own sort of error space, and it will be thrown up to wherever it's caught. Now, that being said, exceptions create certain degrees of non-determinism, where you can't reliably execute code that you could if you use global errors, because global errors don't unwind the call stack. They just return, and then you get control back at essentially the function that's calling into this other function. So I wanted to just share this, is that I think he's kind of making a joke here, but I've created actually a few different exception handling models that are used in large-scale systems, so systems that have millions of lines of code, and that I was able to get them to change from the error no mentality to exceptions for those contexts, because it's more important that they can have multiple threads of execution that will run in a fast, independent way than the dealing with the non-deterministic behavior of exceptions. So I want to be clear here and share that I do not know what the answer is. I don't think it's a global int error no. I think that's not cutting it. But I also don't know that exceptions are it. I understand the frustration and the lack of deterministic behavior, and also just the syntactic clutter. It's very hard to know where to catch an exception and when to. Like, Herb Sutter talks a lot about this. There's like this, it's exception safe kind of thing. And I've spent years looking at this to try to understand it, and I still don't know exactly how I feel. But I just wanted to jump in and say that I can understand why, for soft real-time systems that need potentially deterministic behavior, why exceptions would be unacceptable in that context. However, in places where you are not under those types of constraints, I think that they could make sense. So this is like what I was trying to say earlier about adding just some nuance. I don't think he's wrong, but I don't think that exceptions used in other domains are wrong. Both things can be true.
Third-party libraries, some other third-party code that we have to interact with that's designed around them, so we'll sandbox it off. Templates, while we don't have a hard rule that says no templates, we do have I have a particular face that I might give someone if they use one, and it's not a happy face.
Okay. Mike's definitely not going to like me. So listen, templates can, like exceptions, can be a mixed bag. I want to try to be as fair as possible. I'm going to tell you a little bit of a story here. We're going to meander a little bit. I think I mentioned this to Gutsy David when I got to this point. When I was early in my career, so I've always been kind of wired the way that I'm wired, which I just care too much about tech and stuff that I just want to deeply know stuff. And I was really fascinated by templates simply because of what the promise that they potentially provided was. I didn't start getting into templates because I thought, oh, I can write code that no one will understand and look at me flex. It was that I started to think about what they could do, and I was doing generic programming using void pointers, and I didn't like it. It's so unsafe in my mind, taking a void pointer and casting it, and then the runtime system saying it's casted, but did I cast it to the right thing? I think I did, right? There's just that's a really a void pointer is a very powerful thing that I'm trying to write code where the compiler will be my friend and help level me up. I don't want it all on me. I want to distribute the complexity of writing very challenging code. And I think that for the young people in GTT, it may feel like, oh no, I can handle all of that. And believe me, there was a point in my life where I was like, no, I want to do all of it. And then as I started becoming, maybe I suffered a little bit more. And I wrote a lot of bad code, and I struggled a lot more. I started to realize that, the compiler is your friend, right? Like, type safety really helps. And this is part of the reason why I like templates. If you were to ask me, which would you do, void pointer, generic programming, or templates? 1,000 times and 1,000 times, I'm going to choose templates. So this is the side that I'm in favor of templates. But it's nuanced, and I don't think that he's wrong here. The story that I have is early in my career, I was working at this company and I'm going crazy with the templates, and they're basically getting to the point where they're like, look, Justin, this is before Goju. Look, we know that you like to code and do stuff, so just code and do stuff. And so I would. And I built this one thing. It was what was it? It was an encryption algorithm. Yeah, it was an encryption system. And the reason why I built it using a template is I didn't know enough about encryption, and I thought for sure I would pick the wrong encryption algorithm. And I wanted the flexibility for them to level themselves up and choose a better encryption algorithm or a different one when they got someone that's an expert in encryption, which is not me. So I used like policy-based programming or something is basically one of the things that Andrei Alexandrescu talks about, I think, in modern C++. And the policy was the encryption algorithm. And then I just provided interfaces, which was basically like, it was something like encrypt, I think. And then it was like decrypt, something like this. And then I just made it mandatory. By the way, to make it even worse, is I used inheritance. This is an example. It was a templatized virtual inheritance system. Look, I know. I said in the discussion with Alexei that generally speaking, I think inheritance is a bad idea, but not always. There are cases where I think inheritance makes sense. And using just a 2-class hierarchy where the base class has virtual methods that are pure in that they don't provide an implementation can be a great way to enforce implementation for the subtypes. And so it has this subtype polymorphism, but it's also a parametric, it was a dual subtype and parametric polymorphism system at the same time, right? Now, just to be clear, I could understand this and it made sense to me and it worked. I built it. It worked. I think it used like the Blowfish algorithm, 64 or 256-bit encryption or something like that. I don't remember the details. And then at some point I left the company. So a year later, the company reaches out and says, listen, can you come back and work with us? Because your encryption thing, what did they say? Your encryption thing is broken and nobody can figure it out. So I had written this system that was both subtype polymorphic and parametric polymorphic in the ways I just described, that virtual inheritance, and it was templatized. And they said, we've been having our engineers look at this for 6 months. Nobody can figure out your code. And it doesn't work on like some variant of Windows NT. This is a true story. This is, I'm not making this up. So I said, yeah, I'll come in and take a look at it. I'm sorry about that. We'll figure it out. So I went in and I figured out what the problem was. And the problem was something like they moved up to a 64-bit operating system or something, and so the word sizes weren't the same. I don't know. It was something that was super easy, actually, super easy to fix. And so once I nailed it down, all I needed to do is I just needed to specialize the template to this Windows NT kernel. Literally, it took me an hour, right? But it took me only an hour because I understand templates and I can read template code. And I'm not saying this to flex. I'm saying that they can be very hard. That the rest of the team, the only thing they knew how to do was to invoke my template system, but they didn't know how to actually change the template to deal with maintenance issues that came up. And keep in mind, the template system I built, it wasn't broken. I just want to clarify, it worked. It's simply that they switched to a new operating system, and that operating system didn't have like the same word size or something. So there was a mismatch between that and the encryption bits and like the size of the words or something. So this is the disconnect, is they were somehow like encrypting this on a 32-bit machine, and they were trying to decrypt it on a 64-bit, and they didn't know that they need to change like the word sizes. Again, very simple fix for someone that understands these things. But the challenge that they had is they thought that they could just change the code in the template, which is what they were doing. And that doesn't work, because now they're changing it everywhere. They're changing it for all operating systems, and it worked for all the other operating systems. What they didn't know how to do is make it just work just for Windows NT. So they didn't understand that it worked for all these other cases, and they needed to basically specialize. They just need to like specialize it or do proper if-def WinNT or something. I can't remember the details, but they really struggled to understand how to read the template code. And I do not fault them at all for that. It's very hard. It's like reading lambda calculus, right? It's very hard to do. And so templates can create problems, absolutely. And the way I think about it is very much like how Alexei described it, if I'm just being honest. It's a question of lowest common denominator. I don't mean to sound mean. That probably sounds mean. I don't mean to sound mean. I'm just trying to be real. If you have a team of superstars that everybody in the team is like hardcore coder, templates are probably not a problem. But if you have a team that has people that are, the 9-to-5ers that don't really care about stuff, yeah, templates they'll probably break the team, because people that don't like really want to level themselves up, they'll look at it and it'll be kind of like gobbledygook, and it'll probably create frustration. So, all right, let's continue.
So there's occasionally a good use, but most of the time what it is a poor use. And most of the time it slows things down. Certainly anybody who's worked with templates at scale, where a code base that's heavily relied on them, knows how it cripples compile times.
Okay. Oh, right. So again, now he's not wrong. For those of you that don't know, when you do templates, what it does is basically code replacement or code instantiation. And if you use the templates for a lot of types, it instantiates the code in a lot of places. When you have really fast iteration on development times, like they're compiling and building and doing stuff at a really rapid clip, templates are probably a pain in the ass for them, because they need essentially the compile time to be as small as possible. Yes, right. That makes sense. But again, in cases where you're not doing like 100 builds a day, and instead you're moving, I mean, there's essentially there's ways to offset this. This feels as though it's a little bit more specific to his development environment. So I would argue that while what he's saying is correct, I think that it really just depends on the environment that you're in. And I think there's a reason why the standards template library is all templates, and it remains part of the standard language. That I think a lot of people see the beauty of it and use it. We use it everywhere at Merle, and it doesn't cause any problems for us. I use it in like all over in Nautica. And we also used it at Machine Zone, right? So in our C++ stuff, we had templates. So like, I don't disagree with what he's saying, but I think it's quite contextual, and I think that there's it's important to kind of acknowledge that nuance.
IOStream in particular, while we do use the standard out mechanism for our sort of TTY and debugging info on the console as well as on the development PCs, we don't use the C++ specific implementation IOStream. Multiple inheritance, that's right out. That's not even a question. Like, that's just dumb. Operator overloading. So we don't, again, unlike the JPL project, we don't have a strict rule about no operator overloading, but you will get the frowny face or the angry face, depending on how complex that overloading is. For rule of thumb is if it's super obvious what you're doing, we tend to let it go. So adding a couple of vectors, it's super obvious what that's going to get transformed into. Okay, we'll let it go. But anything sort of significantly more complicated than that will be heavily frowned on.
So, yeah, I think I kind of like his take on this with operator overloading. I tend to only use operator overloading in cases where I think it's super clear. Like I have two matrices, and then I have the plus operator. I don't even know if plus works for matrices. Yeah, it does if they're the same size, right? And so I would overload the plus operator, and I think that's fine. But I have seen people do really not great stuff, right? I think that's what he's getting at is you aren't constrained necessarily in operator overloading to implement the operator in the way that actually makes sense. So you can overload operator plus and have it behave like multiplication or division or like a pointer dereference. And I've seen some people do stuff like this, well-intentioned, like the good intentions. They mean well, but they just like, they're not, I think, thinking through that not everybody is going to have the level of sophistication and education in the space as they do, right? And so they're sort of like let me give you an example. If you have a variable and you add, let's say that you have this variable. This is a variable x. Okay, I'm not going to tell you what its type is. And then I have this, and then I have this. Y is equal to this of this. For those of you that are seasoned in pointers and C, C++, even if you are thinking about like a C pointer or a C++ iterator, this does what it just does basically what you want it to do. It acts as a dereference. You are dereferencing a pointer or an iterator to get its value, right? That's what this is basically doing. And for the experts that are watching this, you probably, I suspect, are saying, yeah, that's sort of what you would use it for. Now, imagine that somebody goes in, and this is a specific type. That's why I didn't tell you what the type of X is. Let's say that it's a user-defined type. So we create our own thing, and now we have this. And they decide to overload the star operator so it doesn't mean dereference. It means something else. Now what happens? Now you have pandemonium, because when you're looking for the bug, people are going to look at this and say, no, that's fine. Let's just keep moving. But it's not fine because somebody overloaded it to do bad things and it's missed. So what I think he's trying to get at is, as long as you follow the sort of general rules of what these operators are supposed to be doing, like you don't overload the is equal operator to mean inequality, or something like this. You don't overload the dereference star operator to mean, I don't know, delete, then you're probably okay. So my high level take is, yeah, my intuition, I actually really kind of like this one. And in fact, I need to think about it more, but it may have actually kind of changed my opinion about the, whoops, what just happened? My opinion about operator overloading and how maybe we should enforce a similar-ish rule in the systems that I'm working on. I quite like it. Okay, I'm going to take a quick pause because I now have to uninstall this thing that keeps distracting me, but we'll be right back. Okay. All right, let's keep going. So I like it a lot. Oh, actually, let me add one more thing to this, because Did we miss? Maybe I missed multiple inheritance when I was thinking, but yeah, absolutely. That one's not super great. I want to just share one additional thing as we're talking about templates, inheritance, and all this stuff. There's this concept of generic programming, right? And the idea of generic programming is you sort of like, you have this algorithm, right? You have this algo, and it does the algo stuff. Whatever algo stuff is, it does it here. And it turns out that algo is super cool, and it helps a lot. So rather than it working with maybe just one type, you change the system so it can work with many types. And at first you realize, okay, well, it should work with integers. And so you make it work with ints. And then you realize, oh, it should work with floats. So then you copy it, and then you make it work with floats. And then chars. And eventually there's so many types that you realize it works with. You're like, wait a second. Like, we just need to stop with all this type thing and just make it work with all types. And that's when we get into this space of generic programming. And in general, so we basically try to abstract out the types. So because the algo has so much use in all these different ways. Now, in general, the way that I think about this in terms of C and C++, generic programming can sort of be done in like 3 different ways. One, you can use void pointers. And by the way, each of these has trade-offs. This is science, right? There's no, you don't get to have your cake and eat it too. There's no panacea. You have to, any decision you make, you're going to compromise something. So void pointers, while they don't have, I think, basically very limited, if any, runtime overhead or compile time overhead, they lack type safety. No type safety. So you could cast into something and be totally wrong and just destroy the operating system memory or something, right? Then you have essentially the subtype polymorphism, which is inheritance. And as we discussed, inheritance can function as generic programming. You have the base class, and then you derive all this stuff. But as he's probably going to get into, this essentially has runtime type information overhead. Essentially, you have to look at things like the vtable and other things that you pay a penalty at runtime. There's no penalty at compile time. There's penalty at runtime, but it's type safe. Okay, so this is like not type safe. This is type safe. In this solution, I think it has runtime overhead to make it polymorphic. And I also think it creates code complexity. Code complex in the tree hierarchy. And then the third type is the parametric polymorphism. This is templates. And templates, they create compile time overhead. They can be hard to read, understand, unless you have a PhD or some nonsense. It's not easy. And yeah, so they also, I think, can create code complexity, but in a different way, I think, than inheritance. I think that I personally believe that templates scale more elegantly as more types use templates than inheritance does. And on top of that, you don't have to instantiate. Okay, I should back up. You do still have to instantiate things. This is a very long topic discussion for us to get into, so I'm not gonna go down this rabbit hole, but I wanted to share this because he's basically telling me in some ways what they're doing. Notice that he's not saying that they're opposed to void pointers. And then at some point, he's going to say that he doesn't use the STL. So I'm pretty sure I know how they're implementing their generics, is they're just using void pointers, which, like I was saying, it lacks the type safety, but it's performant. It doesn't have the side effects of the runtime overhead that subtype polymorphism has, and it doesn't have the compile time overhead that parametric polymorphism has from templates. So, but it lacks type safety. And it sounds to me like he's willing to make that trade-off. Okay, right? And I also want to share that in this context, from his perspective, I think it does-ish make sense. And the reason why I share this, and this is part of the increasing the aperture, what often happens with these games is that there will be some core engine piece that they will take with them, but each new game, it won't be like starting from scratch, but it'll be similar. And because of that, you can kind of get away with void pointers, I think. Whereas if you were reusing a lot of the code, I think the void pointer stuff would, again, I'm imagining what they have inside of their development environment, and they probably have libraries that do their own containers, and they're probably all using void pointers, and people probably break things constantly because of that, but it doesn't inhibit their ability to build or runtime, and so they probably just say, this is what we're going to do. Again, it's just based on the constraints, and so I get it. I personally would, I care, the systems that I build, we care about performance, but I don't, tracking down these types of bugs in extremely large scale software that you have to maintain potentially over decades, I don't know that I'm willing to make that trade-off. Again, this is an opinion, so I just wanted to discuss this because these are some of the challenges with really advanced software development. Is there's no necessarily right solution, except maybe we can say subtype polymorphism using massive inheritance trees is just sort of, don't do this. You can do inheritance a little bit, but if you start making it really complicated, like you're probably just wrong. And that basically leaves us with void pointers and templates. And I think void pointers, personally, is I would rather pay the penalty for the domains I'm in compile time overhead, and know that I get type safety, than have to try to debug a system that is across many different systems, that's massively distributed, right? Because our systems are probably communicating with far, I mean, I'm just speculating, right? There's a lot of moving pieces all over the place, and having the compiler identify these things for us, I think, is how I generally prefer. So I have no right answer here. I just wanted to give some insight into some of the things that he's talking about, that he's sending a message, in my mind, on like how they kind of do generic programming, and the things they kind of avoid is, it sounds like, minimize compile time overhead from templates, but still use them a little bit. Don't use multiple inheritance, because just in general, that's kind of like not smart. And then minimize the runtime type information overhead, which are things like dynamic cast, right? And the reason why is you have a performance penalty, which basically indicates to me that don't use templates that much for generics, don't use subtype polymorphism for generics because they're the RTTI, so use void pointers. Okay, this is probably where I'll end part one, and then we'll continue.